Introduction. Welcome to this detailed walkthrough of a complete off-grid solar power system wiring diagram. In this video, we'll carefully examine each component in the diagram and explain how the energy flows from the solar panels, through the charge controller, into the battery bank, and finally out to the inverter to power electrical loads. By the end of this video, you will not only understand what each piece of equipment does but also why it is wired the way it is. If you're new to solar systems, don't worry, we are breaking everything down into simple, clear language, step by step. Let's begin. 1. System overview. At a high level, this setup consists of 4 primary building blocks. Solar panels, these collect energy from sunlight. Charge controller, MPPT, this regulates charging to the batteries. Battery bank, LiFePO for lithium batteries, stores energy for later use. Inverter, charger, converts DC battery power into usable AC power. Everything else in the diagram, such as fuses, breakers, shunts, digital monitoring panels, and cable gauges, exists to ensure that power flows safely, efficiently, and intelligently. 2. The solar array. On the far right of the diagram, we see 6 Canadian solar panels, each rated at 259 watts. 37.4 volts. These panels are arranged into a wiring configuration that sends power to the MPPT charge controller. The total wattage of the array is listed as white right pointing backhand index 1530 watts. These panels convert sunlight to electricity, producing DC power. The red lines represent positive connections, and the black lines represent negative connections. Notice that the solar panels are joined using combiner connectors, shown in black, before the cables run into the charge controller. This grouping is important because it reduces cable clutter. It protects the system from overcurrent. It allows multiple panels to feed the charge controller efficiently. The diagram also shows the cable gauge, AWG8, meaning the wire is thick enough to handle the expected current safely. 3. MPPT solar charge controller. At the top center of the diagram, you'll find the solar charge controller, labeled AIMS Power MPPT 150V60A. MPPT stands for Maximum Power Point Tracking, which is a smart method for optimizing solar charging. It constantly adjusts voltage and current to harvest the maximum possible energy from the panels. Here's what it does. Accepts power from solar panels. Regulates voltage and current. Safely charges the lithium batteries. Think of it as the brain between the panels and the batteries. The red and black lines from the solar panels enter the MPPT controller. From there, another set of cables, shown again with clear positive, red, and negative, black, wires, run down into the battery bank. The MPPT ensures the batteries receive the right voltage and current, never too much, never too little. 4. Battery bank, lithium iron phosphate, LiFePO4. At the bottom of the diagram are 6 green battery units. They are labeled Valency 27-12XP, 12VDC, 138AH, LiFePO. Here's what that means. Each battery is 12 volts. Each has a storage capacity of 138 amp-hours. They use lithium iron phosphate chemistry, known for efficiency and safety. These 6 batteries are connected in parallel, which means voltages remain the same, 12 volts. Capacities add up. The diagram shows total amp-hours equals 828 Ah. That's calculated as 138 Ah times 6 batteries equals 828 Ah of storage. This is a significant amount of storage, capable of delivering strong daily energy reserves. The wiring of the battery bank is crucial. The black wires tie together each battery's negative terminals, and the red wires tie together each positive terminal. The thick cable gauge labeled AWG4 ensures that the current can flow without overheating. The parallel connection allows white have a checkmark more total energy storage. White have a checkmark longer run times. White have a checkmark even distribution of charge and discharge. 5. Safety components, shunt, breakers, and fuses. Good wiring diagrams include protective devices, and this diagram shows several. On the left side, there's a component labeled BMV703 shunt. A shunt is used to measure current flow in and out of the batteries, acting like a fuel gauge. It sends data to a monitor so the user knows how much energy is left in the batteries, how fast energy is being consumed, battery state of charge. Next, we see breakers and disconnects labeled with part numbers. 8000 for solar disconnect, 409 Quago fuse, 3004 inline breaker, manual on/off disconnect switches. These components protect the system by preventing overcurrent, allowing safe maintenance, isolating faults. Every major power path has a breaker or fuse. Between the solar panels and the MPPT controller. Between the MPPT controller and the batteries. Between the batteries and the inverter. This is proper electrical practice and ensures safety. 6. Digital monitoring panel. Above the shunt, there is a rectangular device labeled Digital Multi-Panel. This unit displays important system information, such as battery state of charge, charging amps from the solar array, voltage levels. Together with the shunt, this allows users to monitor the entire system from a single location. 7. Inverter, charger. On the far left side, we see the large blue box. Victron Multiplus Inverter, Charger. This device has two purposes. Converts battery DC power into AC power, to power appliances like TVs, fans, fridges, and more. Acts as a charger. If connected to the grid or generator, it can charge the batteries. This inverter is connected to two AC breaker boxes. One accepts incoming AC power from the grid or a generator. The other distributes AC power to loads in the building. The thick black and green wires represent the AC wiring, with grounding properly indicated. 8. Power flow explained. Now let's walk through exactly how power flows through this system. Step 1. Sunlight hits the solar panels. Solar panels produce DC electricity. Step 2. Solar power moves through the combiner. Wires merge together. Safety fuses ensure proper overcurrent protection. Step 3. Power enters the MPPT charge controller. MPPT optimizes voltage and current. Ensures batteries charge efficiently. Step 4. Power flows into the lithium battery bank. Stored for later use. System capacity, 828 amp-hours. Step 5. The inverter draws energy from the batteries. Converts DC energy to AC power. Step 6. AC power is distributed to appliances through the breaker box. Like a normal utility electrical panel, the entire process is automatic. 9. WHY Li-FePO batteries were selected. The diagram specifically shows Li-FePO, lithium iron phosphate, batteries. These are superior to lead-acid batteries because they last longer, 10+ years, hold more usable energy, allow deeper discharge, require no maintenance. Lead-acid batteries can handle only about 50% depth of discharge, while lithium can handle 90% or more, giving more usable stored energy. For an off-grid system like this, Li-FePO batteries are clearly the ideal technology. 10. Wire gauges and why they matter. Throughout the diagram we see wire sizes labeled. AWG4 for high current battery wiring. AWG8 for solar wiring. Wire gauge affects how much current can safely pass through without overheating. In off-grid systems, proper wire sizing ensures efficiency, less energy loss as heat. Fire safety. Voltage stability. 11. Benefits of this system design. This design represents a professional quality off-grid power system, featuring white heavy checkmark lithium battery bank for deep storage. White heavy checkmark MPPT controller for maximum solar charging efficiency. White heavy checkmark inverter, charger that handles both DC to AC conversion and battery charging. White have a checkmark system monitoring for real-time efficiency tracking. White have a checkmark multiple breakers and safety shutoffs for equipment protection. This configuration allows full independence from the grid. 12. Final recap. Let's summarize how everything works together. Solar panels collect energy from the sun. Power flows through safety breakers and into the MPPT controller. The MPPT controller safely charges a large lithium battery bank. The inverter converts the stored DC power into AC power. AC breaker panels distribute energy to appliances. This is a full renewable, self-sustaining electrical power system. Conclusion. Understanding a wiring diagram like this gives you insight into the heart of solar power. Every line, breaker, label, and cable gauge matters. Together, they create a safe, efficient, and reliable system that can power an entire home or off-grid location. Thank you for watching or listening. If you found this helpful, please like, share, and subscribe for more solar power education.